Hi Bobcats! In this video we will look at weak base equilibria. Everything that we just did for weak acids has a counterpart with weak bases, but with one big difference. When you write the equilibrium reaction for a weak base, water must be a part of the reaction.
Our objective for this video is to demonstrate how the equilibrium constants for weak acids and weak bases can be used to calculate pH. Our focus is on the weak bases since we covered the weak acids in the previous video. Everything that we just did in the previous video with weak acids has a counterpart with weak bases. There is one key difference though. When we were writing the equilibrium reactions for weak acids, we had the option of writing it with water or without, but in the case of weak bases, water must be part of our reaction. And notice that it is in the liquid phase, and so being in the liquid phase, it does not appear as part of our equilibrium constant expression. But when we're writing the reaction, we have to show it there. There are two classes of weak bases that we will commonly encounter. One of those is ammonia and all of the substituted ammonias or amines that we talked about in a previous video. Ammonia has that lone pair of electrons on that nitrogen atom, which makes it a good Bronsted-Lowry base as a proton acceptor site, or a good Lewis base since that electron pair can be donated to a bond. And then if we take one or more of those hydrogens and substitute them with an organic group, something that contains carbons and hydrogens, we still leave that lone pair on the nitrogen available to act as a base. And so we can substitute one, two, or all three of the hydrogens on ammonia and generate a whole series of other compounds that are bases. And for the second big group, now that we have seen the concept of conjugate acids and conjugate bases, the conjugate bases of weak acids are also going to be weak bases. So if we take something like the acetate ion, which comes from the weak acid acetic acid, or we take the fluoride ion, which comes from the weak acid hydrofluoric acid, these ions, since they are the conjugate bases of weak acids, act as bases themselves. To write our Kb expression, let's take a look at our reaction. We've got B plus water in equilibrium with Hb plus OH minus. And sometimes it'll be more convenient to write this conjugate acid as BH plus. It just kind of depends on the formula that we're working with. If we're working with the conjugate base of a weak acid, that first version, the Hb plus, is probably a good way to go. But if we're working with the conjugate acid of something that we normally consider to be a base like ammonia, the BH plus is probably a better notation. So you'll see that proton added on both sides of the molecule, just depending on the situation. When we write our Kb expression, again, we're going to have the products in the top and the reactants in the bottom, but since water is a pure liquid, it does not appear in our equilibrium constant expression. Let's practice writing a couple of these weak base equilibria reactions and their corresponding Kb expressions. So let's start with ammonia. Ammonia is our classic example of a weak base. When we write this reaction, we have to include water, and I prefer writing it as HOH to show how it breaks apart when it reacts with ammonia. And so we're going to end up with proton transfer from the water to the ammonia. So we will have NH4, and that's a proton coming over with that +1 charge. Since ammonia is neutral, the resulting species ends up with a +1 charge. And then what's left over from the water after the proton leaves is the hydroxide ion. When we go to write Kb for this reaction, we're going to take the products, which are going to be the ammonium ion and the hydroxide ion. We'll multiply those together, and down in the denominator we're going to write the molecular form of the base, NH3, and we're going to leave the water out of it because, although I neglected to write it, water is a pure liquid and will not appear in our expression. Let's take a look at the equilibrium reaction for the acetate ion and its corresponding Kv expression. So the acetate ion is C2H3O2 minus, and it will react with water. Whoops, leaving out that H, there we go. Water, and water will be a pure liquid, and that will be in equilibrium with acetic acid. Now, as I write this, note that we're taking that proton with its positive charge and adding it to the acetate ion. So since it's the acidic proton, I'm writing it at the beginning since acetic acid is an acid. And the acetate ion has a -1 charge, the proton has a +1 charge, so the resulting combination is neutral. And that's going to leave us with a hydroxide ion. When we write Kb, for this reaction, we're going to have acetic acid multiplied by hydroxide and all divided by the acetate ion. And if we wanted to leave this generic, we would probably, we could just use B for the acetate ion and write everything in terms of B. Let's find the pH of 0.025 molar ammonia. Ammonia will react with water to set up an equilibrium of NH4 plus OH minus. And so we'll have our change, and our equilibrium values. Initially, the ammonia is 0.025 molar. For water, I'm going to squiggle it out because it doesn't appear in our equilibrium constant expression, and I don't want to waste any time looking for numbers for water. Ammonium ion initially is 0, and the hydroxide ion initially is 0. So if we calculated a value for Q right now, we would get 0. Q is less than K. The reaction has to go in the forward direction to reach equilibrium. Going in the forward direction means we're going to lose some of our reactants, so I'll do -X for ammonia, and we're going to gain some of our products, so I'll do +X and +X for the ammonium ion and the hydroxide ion. So at equilibrium, we're going to have 0.025 minus X for ammonia, and we're going to have X for both ammonium ion and hydroxide ion. Now, like we saw with the weak acids, the equilibrium constants for the weak bases are so tiny that most of the time we can safely make the assumption that X is small compared to the initial concentration of the base. So I'm just going to go ahead and incorporate that right now and just say assume that X is much smaller than 0.025, and so that's going to lead us to 0.025 minus X is pretty much just equal to 0.025. So our equilibrium concentration for ammonia we're going to use as 0.025 because that little blip that we're going to lose to ionization is so small because it's a weak base. Now, if I go and write my Kb expression, let's see, I'm going to move to the top to write that. We found on an earlier slide that Kb is going to be the ammonium ion times the hydroxide ion, and all divided by ammonia. And I'm going to plug values in for this. Ammonium and hydroxide are both X, so this becomes X squared. Ammonia will be 0.025 since we're saying the X is so small. Let's see, the number that we have for Kb is 1.8 times 10 to the -5. So if I multiply both sides by 0.025 to get X squared by itself, I'll have X squared is equal to, whoops, gotta grab my calculator. That is 1.8 EE -5 times 0.025, and that's going to give me 4.5 times 10 to the negative 7. If I take the square root of both sides, I get x is equal to 6.7 times 10 to the minus 4. I'm going to keep 2 sig figs here because our k value had 2 sig figs. X is also equal to the hydroxide ion molarity. So that tells me that I can calculate pOH. I know the question asks for pH, but we can't get there yet. We have to first either find pOH and then subtract that from 14, or we have to calculate the hydrogen ion concentration and then take the minus log of it. I just think it's easier to take the minus log first, so I'm going to go ahead and calculate pOH. That'll be minus the log of 6.7 times 10 to the minus 4. And so let me hit the log button, and that's telling me that pOH is equal to negative 3.17. The two significant figures in the molarity become 2 decimal places in the pOH. pH will be 14 minus pOH, and so pH will be 10.83.